Okay, let's check the chapter. Oh, sorry. Let's check the chapter of 3.2 measures of spread. Measures of spread. Okay. Okay. Variability is an important idea in statistics. If you were to measure the height of average in your classroom, every observation gives you a different value. That means not every student has the same height. Sorry, something with that. Okay. Okay. And thus, there is a variability in people's heights. If you were to take a sample of the income level of people in a town, every sample gives you different information. And there is a variability between samples too. Variability describes how the data are spread out. If the data are very close to each other, then there is a low variability. What's wrong with that? Okay. And if the data are very spread out, then there is a high variability. How do you measure variability? It will be given to have a number that measures it. This section will describe some of the different measures of variability, also known as variation. Okay. In example 3.2.1, let's check the definition. Okay, here, range. Range is a terminology, is a term of a set of data, is the differences between the highest and the lowest data value, or maximum and minimum values. Okay, range is the highest value minus lowest value. Okay. Example 3.2.1, find the range. Look at the following three data sets. Find the range of each set. Let's check this. The highest value, 50. Lowest value, 10. Thus, the range is 50 minus 10. That will be 40. The second one, highest one, 50. Lowest one, 10. 50 minus 10, that would be 40. The range is 40. And this one, 32 minus 28, the range is 4. Very small, very small. Okay, and now check. When plotting on a paper, mean equals 30, median 30. Why? 1, 2, 3, 4, 5. 5 values. The middle one is 30. Then the range, the largest one minus smallest one, that's 40. Okay, second question. Mean 30, median 30, range 50 minus 10, that would be 40. Look like this. Look like this. The same median as previous one, the same range as previous one. Okay, and next one. Those 5 points are close together, mean 30, median 30, range just 4. So we can observe those 3 data sets. We know, okay, this spread very even, spread evenly, and this one, those 3 in the middle very close, but the small one and big one a little bit far away from the center, and those 5 are close together. Again, the first one and the second one has the same mean, has the same median, and has the same range. The second one and the third one has the same mean, the same average, but different range. Thus, when plotting those data on a on a line, we can see the difference is very significant. Very significant. Okay, let's move. Based on the mean, median, and range in example 3.2.1, the first two distributions are the same, but you can see from the graph they are different. They are different. Okay, and now we have a concept that is called a deviation. Okay, the range doesn't really provide a very accurate picture of the variability. A better way to describe how the data is spread out is needed. Instead of looking at the distance of the highest value from the lowest value, maybe we can see something different. Look at the distance of each value from the mean, and this distance is called deviation. Again, this distance, each data point, the distance between each data point to the mean, that is called a deviation. You must remember this term, deviation, D-E-V-A-B-I-A. Sorry, my English is Taiwanese accent. I think you can understand this deviation. And here, example 3.2.2, finding the deviations. Suppose a vet wants to analyze the weight of cats. The weight in pounds of 5 cats are 6.8, 8.2, 7.5, 9.5, and 8.2. Find the deviation of each of data set value. Okay, and here we know the X bar is the sample average. That is 8.02. 8.02. And now try to calculate the distance between each data point to the mean. Okay, the mean is 8.02. The data 6.8 minus 8.02, that would be minus 1.22. The second one, 8.2 minus 8.02, that is 0.18. The third point, minus 8, and we got minus 0.52. And this, the fourth point, we got the deviation is 1.38. And the last one, we got a 0.18. Okay. And now you might want to average the deviation, and you need to add the deviation together. We put everything together, minus 1.22 plus minus, sorry, not minus, 0.18 plus 0.52 plus 1.38 plus 0.18. We got a 0. Why? 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 Theoretically, the distance should be all positive or zero. Positive or zero. But according to the definition, the point minus the average, we got a minus value. We got a minus value. Thus, the scientists to solve this problem, they use a different way. This can't be right. The average distance from the mean cannot be zero. The reason it adds to zero is because there are some positive and negative values. You need to get rid of the negative signs. How can you get to that? You can square each deviation. Originally, it was minus 1.22, and get a square value, that is 1.4884. 0.18, get a square value, that would be 0.0324. After the square treatment, we got the positive values here. as the values here. And now, average of the total of the squared deviations, the only thing that is that the statistics here is a strange average here. Instead of dividing by the number of data value, you divide by the number of data sets minus 1. In this case, you should be this. Okay. In divided, that is in the denominator, should minus 1. Should minus 1. I should slow down here because it's very hard to explain. Very hard to explain. You need to have a minus 1 value in the denominator. You need to remember this part. Again. The sample numbers are 1, 2, 3, 4, 5. 5Ks. 5Ks. But to calculate the standard deviation or variation in the denominator, we use the number minus 1 divided by the number of data set minus 1. Okay, let me screenshot of this one. Okay, I just took a screenshot and copy paste it to our online group. Again, when calculate the standard deviation, we need use the denominator minus 1. Denominator minus 1. Okay, and notice that this is denoted as s squared. S squared. This is called the variance. And it is a measure of average squared distance from the mean. Now, if you now take the square root, you will get the average of distance of the mean. Again, take a square root of it, and that's about 0.965 pounds. That is a standard deviation. Okay, and now I will screenshot this again. Okay, and this standard deviation is the average distance from the data set point to the mean. It can be thought as how much of a typical data points differ from the mean. Okay, this part is very hard to understand, but we don't need to understand total principles. And here, definition, sample variance. Okay, there is another term called the population variance, but on this chapter, we are focusing on the sample variance. Sample variance, the formula S squared equals summation the square value of each point minus the average and divided by the number minus 1. The number minus 1. Okay. Then definition 3.2.3 sample standard deviation. Yep, this is the most important formula in our course. Again, this is the most important formula, equation or formula in our course. Square root of the x squared. Also take a square root, the bigger square root of the formula here. Again, the n minus 1 on the bottom has to do with a concept called degree of freedom. Basically, it makes the sample standard deviation a better approximation of the population standard deviation. Why? It's very hard to understand, but we just memorize this part. Okay. The n minus 1 on the bottom has to do with a concept called degree of freedom. Basically, it makes the sample standard deviation a better approximation of the population standard deviation. Again, personally, I think this equation, I mean the sample standard deviation, is the top one important in our course. You miss something? Yes. No. I didn't miss anything. But just a reminder, the definition: sample variation, sample standard deviation, population. Okay. Now population with the similar sigma. Where the symbol is the Greek letter sigma, and sigma square represents the sample variance. Mu is the population mean. The big N is the size of population. And now the formula: population variance sigma square equals summation square value of x minus the population mean divided by big N. But in this one, we don't need to care about the degree of freedom. We don't need to subtract it by 1. No, we don't need to do that. Definition 3.2.5, population standard deviation. Take a square root of the value. That's done. Please notice that in the denominator, we don't need to minus 1 for it. No, we don't need that. But in the denominator, we should place a minus 1 over there. Why? Because it has a better approximation of the population standard deviation. Okay, again, if we have enough money, if we have enough budget, we have enough ability, if we have enough time, we can run the test on the whole population. But unfortunately, we don't have enough money, we don't have enough time, we don't have enough budget, we don't have enough manpower. Thus, we need to select some samples to estimate the big population. That is the spirit of the statistics. Okay, let's move. And here, place finding the standard deviation. Suppose that a manager wants to test 2 new training programs. He randomly selects 5 people for each training type and measures the time it takes to complete a task after the training. The time for both trainings are example 3.2.4. Which training method is better? Like this one. Okay, solution. Time to finish a task in minutes Sure, we can consider that if the training is better, the time is shorter. Okay, if the training is better, the time is shorter. Okay, it is important that you define each variable is since there are two of them. Variable one, productivity from training one. Variable two, big S2, productivity from training number two. Okay, to answer the training, which one is better, which method is better, first you need to describe the statistics. Start with the mean of each sample. X bar, X1 bar, the time 56 plus 75 plus blah, 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 and divided by the number 5, we got 60.2 minutes. The other one, put them together, divided by 5, we got the same average time, 60.2. 60 point. Thus, from the average time, it makes no sense. Makes no sense. Okay, then move. Since both means are the same value, you cannot answer which question is better, which training is better. Now, calculate the standard deviation of each sample here. And now, I encourage you to do this part. You may postpone a little bit of time to do that. The first one, square the deviation for training one. Please follow my steps here. Create a new spreadsheet. No, I may have a new one. From here, new one. And new Google Sheet. Okay, and now copy the information here. Copy and paste it here. Oh, okay. 58. I just missed one with 58. Okay, and now, first of all, please change the table like this one. So how to do that? The first of all, copy, and here, click paste the spatial, transposed. Second one, copy, and paste it here. Click the right click on the mouse, paste the spatial, transposed. Okay, the second one. Here, try to find the average of this. Average, you can find this. Okay, and here is training one, the average. And how about the training two? T to average. Here, click equal average parentheses ABE and select the range here. Enter. Yeah, the same average. That is 60.2. Okay, and now try to imitate the formula. Square deviation for training 1. Here, x1 minus x bar 1. Copy. Paste. Oh, okay. Very small. Okay. And here we know click equals this number 56 minus 60.2. Click enter. Yeah, okay, I get it. But no, here we don't know. And next, we do this part. Get the average value minus 4.2 and get it. No, sorry, not average. Get the square value of this. Click here. Click here. Oh. X minus X bar okay, and here is the X minus X bar square. Okay, how to do this? Click here and click equal this one square root ahead and to enter, get it and accept and click here. No, I see 17.64, 219.04. The same one. The same, okay? Okay, sorry, a little bit overuse the time. I think let's stop here. But if you are busy, you can leave now. And if you want to break this one, I will leave here for 5 minutes. Yeah. So see you next time.